Hey everyone, this is Nick Sharp with Radwave. It's been quite a bit since we were last here, but let's take a quick review of what went over last time. So when we last were here, we discussed how Radwave not only allows distributed processing analysis of break-resistant data, but also decentralized in order to share resources like disk space, processing, power, and time. However, at the time, we also discussed how the implementation currently didn't have any security features built into it. So all the connections here, we're using just a standard HTTP, um, and there's nothing kind of built in for data integrity purposes. So I, at the time, really strongly recommended that you only sort of make these connections with people who you knew. So it took a little bit of time for me to iron out all the details, but today we're releasing Radwave 2.0, and this has multiple security features incorporated into it. So today I want to take time to discuss what those features actually look like. So first, let's consider the most simple case for decentralization, where we have two different users. So the first has processed the data and has set up a static file server for the public folder within their local Radwave backend. The second one is using Radwave Explorer to connect to that file server over HTTP in order to actually look at the data. So the first thing that we'll do is conceptualize this first user as an actual HTTP service as it actually is one. So let's take a look at what this really means. Here I've got Radwave running. It's connected to this local host 7398 port. And we can see this list of collections. This is showing the exact same data as what I currently have sitting in this external Lake 3 folder on my machine. Going between these two, we have the exact same thing present. And I can click on any one of these to see what's available. That's right. And if we take a look at what our server is actually running, so I have just a really simple HTTP server set up. This is using just the Node.js HTTP server, just straight out of the box. And then I'm running it, serving this Blake 3 directory on my machine, making that available. And just as we showed, this makes it available for us to connect to. So we can look at our configuration here, and we can see that we're connected over just standard HTTP. It's not secure. And we can even take a look at this in just a standard file browser. So when you start up a Node.js HTTP static file server, all it's doing is making this available to a web browser or to other HTTP connections for us to look at these files on our machine. And we can see here this connection is not secure. And so the first step in order to add some amount of security to Radwave is to start to use HTTPS. And so with HTTPS, it all starts with a certificate authority, and that issues this asymmetric key pair. I know these look the exact same, which implies a symmetric key pair, but we're just going to take these stock icons for a moment, font awesome, and just roll with it, that these are actually asymmetric, which means that they're two different parts. So the server side over here has a private key that it holds onto forever, and then public keys are available on the other side of this. In order to validate the content is coming from this particular server, since these were granted by like a trusted certificate authority, so to be like the Googles of the world and whatnot. The client here can have confidence that the data they're getting is indeed who it says it is. So in this case, this connection between this one server and this one client is now secure. So what this does is it just ensures when you connect to like a known website, anything that you trust by default, that's good. The difference though that we have with Radwave is that we're connecting to all different types or we're connecting to not just trusted servers, we're connecting to uh, different people on the internet who are hosting things locally on their own machines. And so, where a trusted website has business purpose for existence, it has, some need to have customers, and it has content it wants to display for like real meaning for the benefit of the servers themselves. With Radwave, we hope that people are still have that great intent, but at least me personally, if I'm connecting to some random person who alleges to have actual Radwave data and they have mountains of it and they want me to help sift through it, I'd like to have a little bit more of a guarantee than just the fact that they were able to get that they were able to use HTTPS successfully. And so let's take a look just for a moment. Let's kind of think through what I mean by this. So if we have one sort of bad actor on who's using Radwave, who says they're hosting data, and they may have some, but they may also modify something to put malware on it, then the certificate of authority here will, in fact, make sure that this connection is secure, but the data that they have may not be trustworthy at all. So that'll pass straight through this HTTP connection, and it's still not necessarily a trustworthy thing. So with Radwave, we took it one step farther than that. And we've taken some steps to include data integrity of the process data itself. So that way I can have some peace of mind and you can have some peace of mind that the data that's been processed by the server is in fact the Radwave processing and hasn't been modified or tampered with after that point. And so since that's kind of unusual, don't often have data integrity checks happening for this specific purpose, often in applications. Let's take a look at how exactly that was implemented, because it's not all that difficult. It's just kind of unique in this case. So the way Radwave approaches this problem is by using a hash chain. So that's the term that I kind of came up with. So we're basically, we have a number of different files involved in Radwave, as we saw looking at the static file server content that was being served. And so it all starts with the data that we download from the Breakthrough Listen Open Data Archive. So all of those files there, here, let's go to their website. So when we go to their website where this Open Data Archive is hosted, we can see that every single file can be downloaded, has this MD5 sum. So this is a cryptographic hash to validate that the content of the whole entire file is correct. And so when you're obtaining data from a trusted source like Breakthrough Listen, MD5 is a perfectly acceptable way to do this. We don't expect them to be tampering with their own data at all. That would really be that wouldn't make any sense. As a trusted place, as a group of scientists all trying to push us together, MD5 is a perfectly reasonable thing. However, MD5, when so it was found to have some vulnerabilities back in the 1990s, and so if you're wanting a cryptographic hash from a non-trusted party, MD5 is not necessarily one that you want to use. There are alternatives that exist that provide much stronger cryptographic guarantees. Blake 3 being one of them. So Blake 3 is just another cryptographic hashing function. So it also outputs a sequence like this, like a fingerprint of sorts for binary data. But it does so with different means. So I'll provide the link in the video so you can learn up on it. Blake 3 isn't super well known at this point. It's very well accepted, but not exactly well known. And so yeah, you can dig into that and learn a little bit about it. Going back here to what we have with the Radwave engine, where the first step to the engine is downloading data from the open data archive. Then we verify the MD5 sum, so we know it is just good as file. And then we move on to processing the data. So when we do this, what we do is we generate an encryption key, and that's stored centrally within the Radwave servers that I host, in order to make sure that the data that we process stays untampered with. And then we proceed to the prep stages 1, 2, and 3. And throughout this, these stages of the processing here, which is shown on the Radwave engine's progress bar, all this stuff is happening. So we first generate a UUID, and that's stored centrally as well, so that way we can retrieve this particular encryption key. And then the .rdc file, that includes hashes of all of the open data archive files, so when we know exactly what's been included and we can validate that appropriately. Whenever we write or update this RDC file or the checkpoint files, those are encrypted locally, so that way they're not tampered with at all during the processing. And this RDC file contains hashes of the RDM and the IQM, that should be an M there, not an IQS, content. And there, instead of using MD5, we're using Blake 3. The RDM and IQM files contain hashes of the content within the RDS and IQS. So, and if you look at the output that's generated from the Radwave engine, you see that this RDC file is very small. He's just kind of a medium-sized file, and there's several of these RDS and IQS files that get generated that are both quite large. And so so what we've done is essentially formed a cryptographic chain throughout Radwave's processing. So any time we're reading any sort of content from disk, that hash gets verified throughout it to make sure that even while data is being processed, whatever is written to disk is correct. The finalized stage, at that point, it validates the final hashes of all of these, of all the content, and then it centrally stores the hash of the final unencrypted RDC file, and it writes that RDC file unencrypted locally. So at that point, once we're all done with all of the processing, no files are encrypted on your local server. Everything has hashes that have been computed during processing, and that's all stored. And the hashing information is stored centrally within Radwave, so we have a trusted place we can go to know that nothing's being tampered with there. Now, as we move on to the Radwave Explorer, it verifies this data integrity via this hash chain. So we have the first, what we do when we connect to a backend is we get the UUID of each collection from Radwave Cloud for that particular backend. We then obtain the hash of each RDC file from the Radwave Cloud. And then we obtain each of those very small RDC files from the backend and validate that the hashes are correct. Any of them that aren't correct, those aren't available to view. And the memory that the RDC file occupied while it was being processed is wiped. When you go to actually view a collection, there we get those IQM and RDM files from the backend, validate their hashes. Again, if anything isn't correct, the memory that those files occupied is wiped. And then as you're looking through the data, the RDS and IQS content has its hash checked as well. So all throughout this entire process, we're making sure that any sort of data ingest is validated. So this can give me some peace of mind if you want to start processing some of this breakthrough listen data using Radwave and want me to take a look at that data, that would be fantastic. And now that we have these data integrity checks in place, we can do so with some confidence that everyone is acting kindly. At this point, I'm super excited to start digging into the actual content itself, and then helping people get spun up with processing this data on their own, and we can all look through it. So let's connect over Discord for any sort of questions, comments, concerns about how to do all of this processing, how to set up Radwave using HTTPS. Actually, I'll have one more video that I do about setting up HTTPS using dynamic DNS, so that way you can post stuff from home using SSH certificates from a trusted certificate authority. We'll have that in our next video. Thank you so much for listening. And I will look forward to taking through this data. Thanks.